Hey guys, I see that we have folks in the audience. If you can hear me and you can hear, please send a message in the chat. We'll just waiting a minute more and then we'll get started. Okay, I guess we'll get started ahead. Welcome everyone to the second lecture series by SAESAC, second for students by students. For those of you who are attending for the first time, For Students by Students is a new initiative of SAESAC for the student community to engage in gaining new knowledge and to familiarize with frequently used tools. The FSBS lecture series will focus on sharing minor technical skills and knowledge across the students from undergraduate to graduate level that can be utilized in coursework and/or research. Each lecture in this series will be developed and delivered by a graduate student with considerable experience in that area, tailored to AE applications. These lectures will have a new topic every month based on suggestion by students. So for this semester, this is the last lecture series, and then we'll pick this up right back up in January in the spring semester. So for our second lecture series, we have Daewoon Kim from Aerospace System Design Lab. He's a first-year PhD student advised by Dr. Dimitri Mavris with a focused research on model-based certification of passenger aircraft. So welcome, Daewoon, and I'll hand it over to him.
Hey, thanks. We just did a sound test before, so I assume everyone can hear me. So my name's Daewoon, and today we'll be talking about formalizing system engineering principles through MBSE. So two disclaimers before we start. One is I am having someone fix our balcony door right now, and there is a bit of hammering once in a while going on. So if the audio gets really bad, please type it in chat. And also on the same topic, I can read the chat right now on my other screen as I'm presenting. So if you have any questions during the presentation, feel free to just type it in there and I'll address it that way. So let's go ahead and begin. So the agenda today is going to be about MBSE and SysML as a focus. So I was asked by SAESAC members to give a little bit of, introduction on SysML. However, before we go into SysML, I have to first explain the why of SysML, why it's actually important, why it's a thing right now in the aerospace industry, as well as how we can see this moving forward. So we're going to begin the presentation with a bit of systems engineering background about what it actually means to be doing systems engineering, why it's important, and then going into model-based systems engineering, this paradigm shift that we're experiencing in the industry right now, from document-based system engineering to model-based system engineering. Then we're going to actually go into some little basics of SysML. So we're going to go over common diagrams, common elements that you can expect to see in SysML, the modeling language. And then I'm going to walk you through kind of interweaving all of this together, going through the system architecture process with SysML, with a SysML example. So a little bit about myself. Like it was already said in the intro, currently a first-year PhD student at ASDL, almost done with my first semester, and I really thank all the attendees that came out during finals week. And then, let's see. Oh, yeah, my focus research is around the similar topic that I'm presenting to you today about model-based certification of passenger aircraft, specifically commercial passenger aircraft, so Part 23 or Part 25. My undergrad degree was at Michigan in aerospace engineering. During the time I was there, I had an internship with JPL, Lincoln Labs, and SSL. And after graduation, I moved out to California to work at Skybox Imaging. If you've never heard of the company, it was because it was bought out by Google my second month that I was working there. And after the acquisition process, after a little while, I moved back to Michigan to work at General Motors as a transmission engineer. Then I moved out to Ithaca after a few years of working at GM to start my graduate studies at Cornell University in systems engineering. After I graduated with my master's, I moved over to Cambridge, Massachusetts, to work at Aurora Flight Sciences. There, I got to actually experience system engineering within an actual system. And I worked as an autonomy systems engineer on urban air mobility and unmanned vehicle platforms. So, system engineering and the system architecture overview. Why do systems engineering? As many of you guys are aware, as aerospace engineering students, the systems that we work on are really complex, and they have a lot of highly related and interconnected components. It's even across disciplinary areas. The way that you're designing landing gear has a lot to do with requirements that come from aerodynamics, as an example. And system engineering is all about coping with that complexity. The systems that we work on are always going to get more complex because the requirement and demand for them is going to be greater performance, greater robustness, and greater flexibility. And so I really like this definition here laid out by Nkosi, is that by using system engineering approach, things such as project cost, resources, time scale, and risk are managed and controlled by building greater control and awareness of project requirement interfaces, issues, and consequences of any change. Essentially, systems engineering is a discipline of designing with a purpose and designing with foresight. You're designing with what's ahead, making sure that what you're designing actually fits the bill of what someone needs. It is able to interface with whatever its operational environment is, and also it is able to be mitigating the risk as you are designing. So yeah, the motto is don't rely on luck, use systems engineering. So let's go into a greater definition of what system engineering really is. System engineering is an art and science of developing an operable system and capability of meeting requirements. I just like that definition because I like the fact that it describes myself as both an artist and a scientist, which sometimes I consider myself neither. But a systems engineer as a discipline handles a lot of different things through a project lifecycle. I don't know how each of you guys have worked in industry or been through a design lifecycle through a company before, but these are some common things that you're going to see all throughout different life cycles of a project development. So things such as the ConOps, right? System architecture, defining boundaries and interfaces, allocating and managing requirements, evaluation of actual design trade-off, all of these things. All to say a system engineer wears a lot of different hats in different types of complexity and different types of systems, but all of that can boil down to this diagram right here. If you've seen this before, you may be rolling your eyes right now. If you haven't seen it, you will see it in your engineering career many, many times over. It's the system engineering V. It's called the system engineering V because it's obviously in the shape of a V. But how you read this and why it makes sense to what system engineering is that you start on the top left here. So you start the entire product design process by asking yourself, what is the actual need? Now, what is the problem that you're actually trying to solve? And what is going to be the set of requirements that help you solve it? So right now, I'm looking around. I'm not sharing my screen, but I have a coffee mug in front of me, right? My need is that I need some sort of a vessel to hold my liquid. And what I'm going to need it for is that it needs to hold a certain amount of volume. It needs to be around a certain temperature. I want to hold both cold water and hot water. And I would like to have it as a handle or some sort of way that I can grasp it. So that's where the next step in the system V comes in. This idea of a need, what I need, becomes formalized into a set of requirements. Set of requirements such that this vessel must be able to handle liquid in temperature ranges of blank to blank. This vessel must be able to be portable, or even maybe it needs to have a lid, right? And then as you are developing a set of requirements, you are going into actual design. This is where the idea of function and form begin to materialize within system lifecycle. This is where you say, okay, well, with the requirements that I have, what is it that I need the system to do, and how can I make it do that? You get more excuse me. You get more specific in your design as you better understand what this thing needs to do. This is a concept called physical allocation. We're going to go over that a bit later. And then at the very bottom of the V, you're into the detailed design realm. You're in the process where you're actually designing the system to the nitty-gritty detail. You have everything figured out from manufacturing to the smallest component that you need to actually create. Now that's the left side of the V. What's the right side, right? The right side is the verification and validation aspect. So you have to actually understand if what you designed works. So as you are going up, see how as you are coming down, you became more and more specific. It went from black box to white box into detailed design. In the same way, you're going to be doing component testing, you're going to be doing integration testing, you're going to be doing system verification, and then finally, a complete operational verification at the needs level. So that if you have followed this process to the dot, you not only have a system that works and does what you need it to, but you also have verification that it works, and you have a reliable system as an end product. So, in this idea of system engineering, what's system architecture? System engineering can be, I guess, said as the entire process. It's through the entire life cycle. Systems architecture is the first 10 decisions that you're going to be making within the system engineering process. And this is what I'm going to be focusing on today, because this is where I believe SysML or MBSE, whatever you want to call it, that's where it really shines. And I say that because the first 10 decisions that you make, or I guess the system architectural decisions you're going to make in the product, is the most important, and it has the most amount of implication. As an example, let's say you're building a house, right? You're building a house, and so what do you want to know about this house? The first 10 big decisions. One of them is going to be like the location. Another one might be the number of bedrooms. Another one might be a number of floors. The reason that these are the most important things because you don't want to build a beautiful house and then realize you built it on top of a swamp, or you built it in a completely wrong state or in a city. It's gorgeous from the outside and from the inside, but it only has one bedroom. And the cost to be able to change these things later on in the design cycle, once you've already built a house, is enormous. You're essentially starting the whole thing over, which is why system architectural decisions is the most important aspect of system design, and this is where MBSE really shines. In a more formal definition, architecture is mapping a function to form. These two definitions are a bit important because they're going to come up throughout the entire presentation. And it's one of those words where if you ask 10 engineers what function means, you're probably going to get 11 different answers. So for the sake of our presentation, function is simply what the system does. It can be a process, it can be an operation, action even, but essentially it is the byproduct of this system. And then the form is what the system is. So the form can be physical, it can be logical, it can be a piece of software, right? It doesn't have to be an actual thing, but the form is what what initiates and causes the function, and function is what gives form purpose. And connecting those things, mapping those things together is the architecture's main role. So, system architecture process. If you see this shape, you're going to see it's a bit familiar. That's right, here it is again. It is a system engineering V. And it's the first, right here, like 3 segments of it. So you're not actually getting down to detailed design yet, but you are going through this cycle where, 1, the first step is stakeholder analysis. You're asking yourself the question of what do my stakeholders need? What do either the users or the people who are paying for it, what are the ways that actually the set of requirements that are placed on the system by them? As an example, you're designing an aircraft, right? You're designing a commercial aircraft. Say it's the next middle aisle aircraft, next generation NMA for Boeing. One of your key stakeholders is going to be the FAA because they're going to be the ones who certify your vehicle. and they have a very stringent and formal process of having a certification plan, and they have a set of requirements as formalized documents. And so understanding and deriving requirements that are applicable to your system out of that's part of stakeholder analysis. The next part is concept exploration and selection. So this is where you're exploring different concepts based on the needs that you have, and you are trying to stay solution neutral at that point. So what do I mean by that? So let's say the need that you have is, I need to get to class from my apartment. Well, you have multiple ways to be able to do that, right? And maybe let's add a requirement in there. You have to be able to travel 1 mile in 10 minutes. So certain concept exploration, you may be led to say, oh, you need a car, right? But there's other alternatives. Car isn't the only mode of transportation that's out there. It can be a bike, it can be a scooter, it can be your Heelys, it can be a really nice pair of running shoes. All to say, different concepts that meet the needs are explored in this. And then once you have actually down selected, there's different methods to be able to do this, things such as morphological matrix or AHP. But essentially, you get down to it, and after you've left this block, you have a better understanding of what your system is. You know you're building a plane or you're building a scooter, right? And then the functional architecture is the next step. This is where you're asking yourself, okay, what does it actually need to be doing? Then the physical allocation, this is the form. So function and form, mapping this here. The physical is, okay, what is the architecture actually going to look like? And then you finally select architectural traits. Because at this point, you probably have multiple different physical architectures that is possible with the given functional architecture. And then you do a down selection based on it. You may even be led to go back all the way to stakeholder analysis if you don't have any feasible architectures. But nonetheless, you move on, and then you have selected a top level architecture, and you've answered the top 10 questions, or the first 10 questions of a system engineering process. So that's system engineering in a nutshell. Now let's get into model-based systems engineering and what this means. This has become a real buzzword in the industry recently. I'm sure many of you guys have heard it or are already sick of it, but there is a real good reason for that. So what is MBSE? Model-based system engineering is a formalized application of the modeling to support system requirements, design analysis. Essentially, it's a formalized application of using digitized models to be able to support system engineering. Here's the V again. The system engineering process, which has been followed for generations now, is actually going digital. Previously, what would have happened is all of this is done via documents. You have a set of requirements in a separate document. You have your functional documents, you have your physical documents, right? You're designing a component. You have your CATIA model, you have your hardware model, and then whatever it needs to be actually doing, you have your Simulink block in a different software. All of these things are crossing over boundaries, and there's no interface between them. And it is all controlled via documents. This becomes really true, especially for aerospace engineers when you're doing aircraft certification. Right now, it's all document-based certification, as in you have to show physical documentation of test results of your aircraft meeting requirements and certification standards. To bring all of that into a holistic environment and to be able to do that all interconnectedly, that is what MBSE is all about. And it makes a lot more sense because our systems are increasingly becoming complex. Hardware and software is becoming this out-of-touch reality of what we think about. And so just as an example, right? Let's say you're designing the next Apple Watch. You're not just designing a watch that interfaces and keeps time anymore. This watch needs to be able to be talking to your computer, your TV, your thermostat. It becomes where what you are designing plays a much bigger impact. It integrates into a much greater environment that you can wrap your head around. And so document-based engineering is becoming outdated, and model-based system engineering is coming into trend. So this is where SysML is coming into play. SysML is the general purpose graphic modeling language to be able to do MBSE. Excuse me. So you have these process standards that have already been out for very many years. And you have things such as modeling methods, right? You have object-oriented or structured analysis. And then you have things such as architectural descriptions and framework. Beyond that, that's where you have modeling standards. Many of you guys might be familiar with UML if you have software development background. Essentially, it's the idea that you have a formalized language, formalized process, or not a process, a formalized understanding and methodology to provide a graphical representation of some of the semantic foundations of MBSE and systems engineering, such as requirements, behavior, structure, and parametrics. Many of these things we've already talked about, right? We've talked about how requirement fits into behavior being almost synonymous with function, but a bit beyond that. Structure, the form aspect, and then parametrics, what the actual values these structures bring into the system. And then integrating all of these together. This is where the strength of SysML is coming into play. To draw your attention to the chart on the right, like I said, SysML is actually an extension of UML. So UML already has many of these diagrams, as you can see by the key. However, SysML builds upon that so that it's not just applicable to software development, but over a much more wider general system development. And then the two new diagram type that's been added is requirement diagram and parametric diagram. Requirement diagram obviously is really important because you have to better understand what your system is being designed to. So SysML just brings requirements into the same environment as the rest of the model. And then, so previously, requirements would be kept in something like doors, for example, and then UML would have an interface to doors so that there's traceability from an external software, but SysML just brings it into the same environment. And then parametric diagram. We're going to go over in more detail what parametric diagram is. But once again, it's an additional interface that SysML has to all the other disciplinary analysis tools. So this is the the no magic MBSE grid. Different SysML APIs will have different ideas of how this is going to look. Different companies are going to have different understanding of how this is going to look. But the general principle stands the same. And a lot of this, once I explain it, is going to sound very familiar. So for a second, let's forget that there are 3 rows here. So we're only looking at the first row. These are the 4 pillars of SysML. Requirements, behavior, right? Here we go. Functions, use cases, and then structure. This is the form, and then parametrics, the actual value of the system itself. And there is a linkage across the board, across the row here. And so that's the very black box approach, and this is just going right down the V, just as we've been talking about. SysML adds an additional layer to that by adding additional rows or layers of abstraction. Why this is important is because the system that you're managing is really complex, as in you can't just have a singular row where all the requirements that you have are in a flat structure, all the functions you have are on flat structure. You need to add hierarchy to it. If you're building an aircraft, the black box top level system might be something like an aircraft, right? But then you have the aircraft subsystem. You have avionics, you have power plant, you have airframe, whatever it is. And those have a set of requirements which ultimately derive up to the system level requirements. And then even beyond that, you have battery requirements at the component level, maybe even further, right? All to say, it's not just 3 rows, it decomposes as much as you need, but every layer you go down, you're becoming more solution focused. The further up you are, the more solution neutral you are. The further down you are, the more solution specific you are. And at this point, you are doing component analysis. You have like very specific equations, set of equations and constraints for what your system is being designed to and what your component needs to do. Why? Because the layers above it have helped to define it. So SysML, some common things that you're going to see a lot. Every SysML diagram has these things called frames. So this box would normally be bigger because there'd be content inside of here. But this header right here holds some useful information. First thing is, it tells you what type of diagram it is. We're going to go over all of these different type of diagrams, but it'll say ACT or BDD, so activity diagram or block definition diagram. It's also going to have what the model element is, the type of model element it is. So it's going to say like it's a package, it's a block, and then it's also going to have the element name. And then you can also give it a user-defined diagram name, so just like a nickname or indication of what you want to just call the diagram. But all of this information is available at every single diagram. It doesn't matter what type of diagram it is. The header and this type of a format stays the same. Another basic thing that you're going to see very often in SysML are blocks. Again, if you're familiar with UML or software development, blocks are very similar to, or almost synonymous to class. Essentially, it's a unified concept that describes the structure of an element. And it can be assigned to a type of element, but it can be anything. It can be a system, it can be a hardware, software, it can be a procedure. In this case, it's a centrifugal pump. It's a physical form. Excuse me. And then you have, so let's go over some of these compartments that it has. Not every block has every compartment, but these are just some ways that you can begin to describe and define your block. So constraints. Constraints mean that it is assigned with a constraint block or a set of equations. So the pump efficiency or the efficiency equation is attached to the centrifugal pump, which makes sense. Parts are just as it sounds. It is decomposition or the one layer down of the different ways or subsystems that this block is made up of. So a centrifugal pump is made up of impeller, seal. It looks like it's made up of 3 bearings and 2 O-rings. So things like that. And you would expect to see more and more parts higher up you are. And then these parts themselves are actually going to be blocks. So there's going to be an impeller block that decomposes down from a centrifugal pump. And maybe the impeller has some parts, and so on and so on. And you are building a block hierarchy. References are just other blocks that this system interacts with, but it doesn't necessarily own it. So obviously a centrifugal pump works with fluids. It also looks like it works with lubricants, but it doesn't own the lubricant. In this way, you own the shaft, you own the impeller, but you don't own the lubricant. And then the values, some parametrics or characteristics of the pump. In this case, looks like all it cares about is its weight. So this is a block, and you're going to see this in almost every diagram in some shape or form. Okay, so let's go back to the 4 pillars. So the first pillar is requirements, right? We've talked about requirements enough, but let's see it in action in terms of SysML and what it looks like. A requirement stereotype is a text-based requirement. Essentially, all it has as a SysML default is an ID and a text. So you can see an example here. Well, actually, let's go back from the beginning. Looks like the highest classification is a hybrid SUV specification. This specification has 2 different types of requirements. There's eco-friendliness, some green requirements, and then a performance requirement. The green requirement has inside of it an emission requirement. In this case, the emission requirement is that the vehicle shall meet ultra-low emission vehicle standards. Not the best requirement, but there it is. That is a requirement. And let's see. This one doesn't have any relationships to it, so let's go over here. The performance requirement, there's braking requirements, there's acceleration requirements. And if you look at the acceleration requirement, it looks like there's some relationship to other elements. So there is a power requirement that's actually derived from the acceleration requirement. So that's a type of relationship that you can have. There's a verification relationship where this acceleration requirement is verified by a specific test case, in this case, a max acceleration test case. And then the power requirement is satisfied by a form, in this case, a power subsystem. So there's interwovenness within SysML that doesn't have to be visually shown, but nonetheless, it can all be built into the model. So that if you were to change the power requirement, the power requirement goes from available 5,000 kilowatts to 3,000 kilowatts. Then there is a linkage already to the acceleration requirement, and SysML is going to catch that. It's going to run a change impact analysis to be able to say, hey, you made a change and you have a delta in your power requirement. This is going to impact two things that it's touching. It's going to impact the acceleration requirement, and it's going to impact the power subsystem. Is that okay? So these are the ways that SysML helps with system engineering and helps by managing complexity. Okay, so that's the first pillar, requirement diagram. The second pillar are behavioral diagrams. Behavioral diagrams can be done in 4 different types of diagrams: activity, sequence, state machine, and use case diagrams. The key thing I want to iterate here is these diagrams may look different, but they serve the same purpose. Not that you only need to do one, but you need to use them they complement each other, but you have to use them rightly and in the right situation. So let's dig a bit deeper into what that means. Activity diagram. This is something many people will be familiar with. It kind of looks like just a flow diagram, right? And that is what it is. It specifies transformation of input to output. It works as a gigantic function block, right? You have some sort of input that's feeding into an activity or a function or behavior here. Looks like there's another input from external to the system that's coming in. But you start the activity here. There is a straight divide into A1 and A2, activity 1 and activity 2. Following activity 2, there's an output that's going out of the system. There's a decision node right here. There's a split. Let's say X is greater than 0, and then A3. It combines with a flow from A1 and et cetera, et cetera. And you have an output, and then you have a finished node. And then this would be an activity. This is some sort of a process that is describing a behavior. You can fill these A's, I believe, yeah, there we go. Here's a better example. Well, let's say you're trying to operate a car, right? You turn on the key, and immediately as you turn on the key, it sends a signal to both the braking activity and the driving activity. It doesn't necessarily mean that you're braking, as in this activity is doing anything, but it is sending an activation signal, or also called a token. It's passing along a token. And then the driving passes along an actual object or a signal, in this case, brake pressure. So when brake pressure is applied while you are driving, there is an obvious pressure that's sent to the braking, but it also sends to the control operator, which enables the braking once the pressure is greater than 0. So driving sends a brake pressure. As soon as pressure is greater than 0, it monitors traction and initiates a braking sequence. Pretty simple. And this will be the activity of operating a car. And also, if there is a signal to turn the key off, then immediately exits out because you are no longer operating the car. Second type of behavioral diagram is a sequence diagram. This one is actually a lot easier to read, despite what the diagram looks like, because it's always read from top to bottom. Whereas, this is, you have to follow the arrows. This is always just read from top to bottom, and it is set in almost a sequence of time. So you have the driver, and then you have the vehicle. And this line right here, this is called the lifeline. And essentially, all the blocks or these sequences that the lifeline touches, then it is being executed by this individual or system. So both the driver and the hybrid SUV start the vehicle. And then looks like there's a parallel block. So in parallel, you are both steering and you are also controlling the speed. In controlling the speed, you have 3 different modes. You have idle, accelerate, and brake. Do you see that this block right here is divided into 3 compartments? So PAR means parallel. These 2 compartments are working in parallel. Alt means alternatively, so it's kind of working like a state machine diagram. And so there's an idle state, there's an acceleration state, and then the braking state. And you jump between them based on some sort of sequence or maybe some sort of a trigger. It's not specified in the sequence diagram, but nonetheless, you jump between them. And then as soon as you park the vehicle, then you exit this. Fairly simple. So here's the third type, the state machine. It's perfectly coming right after sequence diagram because we just talked about the 3 states. We talked about the 3 states in the operation called idle, braking, and accelerating. Key point here, note that it was apparent from the sequence diagram that there are 3 states and that there is some sort of logic to jumping between them, but it doesn't specify how. The state machine does. The state machine shows that you can go from idle to accelerating when there is an accelerate command. You can go from cruising to braking when there's an engage brake command, and so on. It is jumping between the states. You can only be in one state at a time, but the state machine is able to show that. It's able to show this level of detail that wasn't possible in a sequence diagram. But a sequence diagram is also able to show a level of detail that the state machine doesn't. The sequence diagram, for example, is showing that in parallel, as you are controlling your speed, as you are in these states themselves, you're also steering. State machine can't do that. State machine, you can only be in one state at a time. So there's no idea of the steering mechanism that's happening. So these 2 things are working to complement each other. And then the final and 4th behavioral type of diagram is a use case diagram. The use case means that a system is defined, the boundaries of a system. So this is the hybrid SUV. And then it shows external actors, such as a driver. Other additional actors might be like other vehicles, roads, cross signs, whatever it may be, parking structure. And it has some sort of an activity that it's initiating with the vehicle. In this case, the driver can park the vehicle and the driver can drive the vehicle. The flat tire is, so these are different activities that can be included or extended from it. So obviously driving the vehicle includes steering, includes braking, it includes accelerating, and so does parking. So once again, I'm going to reiterate on the idea that these different types of diagrams are used in unison to show different details of the design. In this case, it's showing that the driver is not part of the system, which is actually a very key idea that was not introduced in any of the other behavior diagrams. It even shows that different activities or use cases have relationship to each other, which is not very apparent in any of these diagrams. The third pillar is structural diagram. Like behavior diagrams, structural diagram have multiple type of diagram types that also show different levels of detail in system design. Start off, you have package diagrams. Package diagrams are synonymous with just folders. You can tell by the way that it looks. So it's just an organizational structure you can do in SysML. All the diagrams that you have, you can order them by diagram type, right? Use cases, behaviors. You can order it by level, increasing hierarchy, or by IPTs. You have structure guys, you have your aerodynamics guys. Whatever it is. I'll say packages are folders. And then structure really comes down to it, and you start to see SysML at play when you're talking about BDDs and IBDs. Remember, blocks are the building blocks. Sounds a bit weird to say, but blocks are the atoms and molecules that form a SysML model. It is showing here the relationship between blocks, and that's exactly what BDDs do. So let's take a look at what's happening here. This is the system of interest here, an anti-lock controller. And this is a relationship called a decomposition. So an anti-lock controller decomposes or is a parent to a brake modulator and a traction detector. So these aren't separate and independent blocks. These are actually children to the anti-lock controller. they are realized. This is a realization relationship as hydraulic valve, electrohydraulic valve. As an example, brake modulator is a logical block. What I mean by a logical block is it is not specified to a physical component. I'm just looking at things around my room. A logical block might be a book, right? But a physical realization of the book might be the Aircraft Design and Conceptual Approach 5th edition by Daniel P. Raymer. That is a very specific book that I have in mind as a form, but the logic of it is that it is a book. In the same way that a brake modulator is a generic logical idea of a brake modulator, a very physical realization of it might be an electrohydraulic valve. So, what becomes apparent in this BDD? One is that these are logical blocks that are parent to anti-lock controller. Now, an IBD shows a layer underneath that. IBD stands for internal block diagram, which is exactly what it sounds like. IBD is assigned to a block. So you have the anti-lock controller here as a block. And if you build an IBD underneath it, you have the two parts. So remember how we said traction detector and brake modulator are children of it? That's why it's under the IBD. These are the different parts of an anti-lock block controller. And then IBD is able to show the relationship between the two. Whereas here, you can't actually see that there's a relationship between the two. You can't even actually see that the brake modulator and the traction detector interplay with each other. But then in the IBD, you're able to show it. It looks like there's some sort of a connector. Each of them have a port, and there's some sort of an item flow between it. A question by Samuel says, so the brake modulator is more of the function and the form is the electrohydraulic valve. Close. Brake modulator is also a form. A form, like I said in the beginning, can be a hypothetical form, a logical form, or physical form. The function of a brake modulator would be it's gonna sound dumb, but it's gonna be to modulate your braking, right? And what component or what form actually modulates a brake? A brake modulator modulates a brake. And then it's realized in a physical form of an electrohydraulic valve. Another example might be, a microwave, right? A microwave is a really classic example that comes up in SysML. My function is to heat food. My system is going to be some sort of a heater. I don't know what it is yet, but that's the logical form. It's a heater. And then what's the physical realization of it? It might be a specific wire coil developed by GE. I'm going to just make up a name here, the GE 4000 wire coil. And that's the physical realization of a logical block, which is a heating element or a wire coil. I hope that clarifies it a little bit. If it doesn't, when I get to the example, it should be a bit more clear, this relationship between logical and physical. And then finally, the fourth pillar is the parametric diagram. So this is actually really interesting, and this is where a lot of meat and value of SysML come into play. As you can see, when I'm talking through all these diagrams, a lot of people ask the question, okay, so what? A lot of these diagrams already are developed. People use like Visio, people use PowerPoint diagram. I'm sure you've seen it, right? Like, where's the value in all of it? Yeah, you can connect it. There's a little bit of play, like you can trace it to requirements. But when I'm designing a system, I want to do detailed design, right? I'm doing CFD, I'm doing load analysis. I need, like, that's where the real design is happening, or that's what engineers say. Like, this is where real design is happening, and I need to be able to interface with that. Parametrics is actually that. It's the interface between SysML, the system design model, and then the actual parametrics and equations that this system is under. So as an example, the straight line vehicle dynamic block, right? This is a value binding block that can be found within the braking system. And it is abiding by 4 different types of equations: the braking force equation, acceleration equation, velocity, whatever it is. And you can see that these equations are also fed in by different ways. So as an example, this mass rollup, you have a kilogram that's coming in here, right? This can be a mass rollup through an Excel document. It can be from your CATIA model if you're able to set up that interface. In the same way, a velocity equation, the second here, maybe this is from a specific test, right? Or a set of simulations that you're running. You're running a glass box example of an aircraft, and you have a data output that also sends your position and time. And you're able to feed that straight into your SysML and have a direct interface with it. And so why is that important? Because you're going to have requirements of all of these things. You're going to have a braking requirement. You're going to have an acceleration requirement. And by tying these elements together, you are able to join this idea of test results, test analysis, or analysis results, and tie that all the way down to requirements to be able to do the right side of the V. You are verifying your design as you are going and as you are developing your analytical models. So I said a lot of things. If you're not familiar with SysML, you're probably very overwhelmed at this point because a lot of these diagrams look boring and they look very similar. So let's go through an example of how they actually work together. We're going to build a digital thread through MBSE. Last definition, a digital thread is a framework that connects information and information flows between the system. Essentially to say, these are things that you will see in your system design. You're going to see requirements. You're going to see mechanical models, electrical models, right? Source code, the product, the test. All of these things need to be working together and talking with each other. This becomes really important because essentially all models are wrong, but some are useful. And in order to make them actually useful, they have to be collaborating across each other. I don't want the mechanical guys designing a completely independent system that doesn't verify the system requirement. I don't want electrical models that look great on paper, but doesn't actually work or verified, or they are not verified by the test, or they don't fit into my project plan. So by connecting all of these elements together and sending data and information between them, you're able to have a singular source repository. The structure guys know exactly what they need to be building. They know exactly the requirements that they're doing. And they know that if they are to, let's say, decrease the size of the bottom hull in an aircraft by 5 by 5 meter cube of surface area, they know that it's going to be impacting the electrical guys because the power plant has a dimensional constraint as well. So something like that. You're able to run a change impact analysis to the design changes that you are making. And essentially, if you set up your MBSE environment correctly, you can input requirements, you can input test results, you can input operational concepts, and it is going to output things that you actually care about and you want to know. It's going to output product specs, it's going to output the fact that it's verified, it's going to show you a collaborative environment, all of these things. And it's going to go to the people that actually matter, the key stakeholders, whether it's suppliers or the design team or the customer itself. So let's look at an example. Here is a TCAS. There is an operational view of a TCAS 2. So TCAS is a traffic collision avoidance system. If you guys are not familiar, essentially it is a box that prevents mid-air collisions, and these airplanes are talking to each other. So for example, aircraft 1, oops, where's my mouse? Here we go. Aircraft 1 and aircraft 2, they are about to collide mid-air. Their TCAS are talking to each other and saying, okay, I'm going to go up, you go down. And then this one say, okay, I'm going to go down, you go up. And then there we go. So you never run into a situation where they're not communicating and then they both go up and end up crashing anyways. Looking at the operational view, it has a resolution advisory zone, and then there is a traffic advisory zone, and then there's a wider zone called intruder. The details of how TCAS works here is not really important, but all to say that there are specific requirements that you can get out of this operational view. There's a certain range of the resolution advisory zone that needs to be defined, and the TCAS must work within this zone. Same with the traffic advisory. There's a plus or minus 850 feet. other information that you can gather from this, it has to interface with not only other TCAS2s, but prior versions of TCAS, so TCAS1. And then this is your system of interest right here, the TCAS2. Oh, also there's outputs and inputs, right? So that's also another requirement that you can gather from this OB1. So that's exactly what we just did. We have a concept of operation. We have a need that needs to be met. Airplanes shouldn't be crashing into each other. We have a set of requirements. They need to be talking. It needs to be a collaborative thing. Again, don't crash my airplane. You have a set of functions that you can start to define. And then you go into detailed design. There's an integration of that. And then there's a verification of that. So I'm going to show that right now on how that is done through SysML. So right here, if you remember what this is, it's a use case diagram. Here's the pilot who's outside the system. They are providing information to this use case. So a top-level activity here. And the top-level activity of a TCAS is avoid in-flight collision with other aircraft. Makes sense. There's an interface to other systems. So in this case, external systems such as the host aircraft. The system is TCAS. It's not the aircraft. So it must also interact with the host aircraft. But the aircraft is external to the system. It also needs to interface with other TCAS from the threat aircraft. There's traceability to different requirement blocks. So these are specific standards. But again, all to say that you see the interplay between things. You see external systems that somehow traced over to requirements. You see the way that the pilot interacts with the system at a very high level and how this actually impacts the system. So we're going to go deeper, decompose what this activity means. Avoid in-flight collision with other aircraft. And what that looks like here, we happen to do an activity diagram where you are the threat aircraft broadcasts a message, and then your TCAS updates the address list. There's an interrogation process, a little bit of a back and forth here, and then eventually you add by adding a resolution. And then over here, this behavior is further solidified in detail with a state machine diagram. A TCAS has 4 operational modes. Oh, it has 4. This one only lists 3 for some reason. It's missing the transponder mode. I'll say there's a power off mode, there's a standby mode, there's an automatic mode, and a traffic advisory only mode. In the automatic mode, you see that this right here, this activity, is located to the automatic road. So in this state, when TCAS enters into the state called automatic, it's going to execute the sequence of events. Here is the form aspect. TCAS decomposes into major subsystems, such as its antenna, its computer unit, control panel. I'm going a little over on time, so I'm going to go a bit faster. So this is the block. This is the physical form of it. The logical form of it. And then this TCAS has, again, the different state machines, and the state machines have the trigger. So how do you get from standby state into the automatic state? You do it by having an automatic mode command. Where does the automatic mode command come from? Look at this internal block diagram within the TCAS block. It looks like that signal actually comes from the pilot. So there's a traceability of the signal being fed into the TCAS. Where's it coming from? It's coming from the pilot. And when that happens, it triggers a state change. And as an IBD, here are the different subcomponents under the TCAS and the way that they have relationship with each other. So let's see what happens. You are executing the state machine, and then you receive an automatic mode command from the pilot. So you're in standby, and then suddenly the automatic mode command came in, so you are in automatic. Automatic, do automatic operation. You execute the automatic operation activity, which happens to be this. And the first command within this is to broadcast a message. So TCAS2 broadcasts a message over, the threat aircraft broadcasts a message over to TCAS. And then the TCAS updates the address list right here, updates the address list, and then sends an interrogation command over to the threat aircraft. In the same way, you can see that it's in play right here. This broadcasting of message is done here at the broadcast message. So I hope at this point, even if you don't have like a mind map in your mind, that sounds redundant, but even if you don't have a mind map that you're thinking of, you can see that these different diagrams have elements that are interconnected with each other. This is why system engineering is so difficult, because you don't understand that a state machine change or an initiation of a certain sequence triggers all of these events. But a proper SysML and model-based system engineering approach helps to interconnect all of these things so you have a much better understanding of a perfect model. Well, you're never going to get a perfect model, but a model that actually captures what happens when a certain sequence of events happen. And you can verify that the system that you're building does what it's supposed to do. Okay, so the previous question about the idea of form and function, logical versus physical. So this is what we just went over, the behavioral aspect of it. This is the TCAS block. This is a logical block, and it's made up of these logical components, directional antenna. The physical realization of it would be the Honeywell TPA 100B, the actual like physical TCAS system, the computer developed by Honeywell. So this is a physical form. This is a logical form. These are the functions. All of these things covered here. This is what the TCAS is supposed to do. So these functions allocate to the TCAS block. In this case, it's a logical block, and it is realized by a physical block. In this case, a Honeywell TPA 100B. These are just alternative physical TCAS systems as well. Okay, there's an aspect of SysML. Obviously, you can't just do the left side of the V. You have to do the right side. So you can build in test requirements. This is actually where it gets really fun, because you can build a test environment here. So let's say you're doing like a hill test. You're doing a hardware in the loop test. You have the threat aircraft simulator. You have a data bus recorder, and you're having it execute the exact same functionality as you would in a real life scenario. And you're able to see that. You're able to see that, okay, the threat aircraft simulator is going to broadcast a message. The data bus recorder is going to record it. There's an update to the address list, and then there's an interrogation process. You're able to verify that your test environment is meeting the same functionality that a real life, an actual flight unit of a Honeywell TPA would be doing. And so you are able to, one, verify that your verification method actually makes sense and it's testing the right thing. And two, that the system verification or the test architecture that you have set up actually works and actually makes sense and actually talks with each other. There are ways to actually automate this in SysML. There's a level of automation in SysML as well, which becomes really critical because you don't want to keep doing these things for the sake of being in SysML. So what I mean by that is we still live in a document-based world. People want outputs not in SysML models, but they want it in Word and Excel. And so there's an actual automated document generation functionality within SysML. There's also an API so that you can have actual specification and build upon the SysML language that's already there for the user. Yeah, exactly. Like I was talking about, you can create domain-specific language. There's a standardized model language, and then there's a domain-specific language. And so you can cater your SysML to your domain-specific language. You can add in extensions. You can add in, just an example, you can add in an extension to the subsystem called a unit under test and be able to trace it to something like a test mode, whereas this type of relationship may not exist in the core SysML model. But you can bring in domain-specific language because there is an interface to an IDE and an API. Finally, model verification. Let's just tie it all together. You can do this within the SysML model called the meta model perspective, where you are seeing the interplay between all the models that you have. So you have all these different diagrams. You did the job, you did system engineering the right way, and you've developed all these models. How do they actually work together? Here is like a bird's eye view mapping of how they work together. Here's the actor, here's my use cases. They help to refine these different types of diagrams, etc. And you can actually add hyperlinks to all of these and like click through it within the model, and it makes it really neat, great for a demo. So that actually wraps up SysML. What I told you today is in no way the complete view and functionality of SysML, but it starts to scratch the surface. It actually starts to point at the need of model-based systems engineering and also points to some of the basic tools. However, there are a lot of really great tutorials online. If you use Magic Draw, Cameo, whatever you end up using, it's perfectly fine, and they have really great tutorials that are built in. If you're looking for some literature, there's the Practical Guide to SysML and SysML Distilled. These are the two pretty much gospels of SysML language. And then if you want to learn more about the system architecture process, there's a really great book by Crawley and Cameron and Selva called System Architecture. Again, there are a lot of really great tutorials online. One by the OMG, it's done by the exact same guys that wrote Practical Guide to SysML. The SI Engineering Handbook is a really great read. And then also there's a class taught by Dr. Mavericks called Intro to System of Systems Engineering. It's not about SysML. It's more about what it means to design complex and interwoven system of systems. But it's a really great expansion if what you heard today is something that you want to dig a bit more deeper into. So yeah, that's it for my presentation. I'll leave it open to questions. But if not, I'll hand it back to the host.
So yeah, we have time for a couple of questions if anyone has any. You can always email Daewoon if you have any additional questions about resources. So with that, please type your question in the chat if you have any.
All right, I'll take that as good. Yeah, I'll take it as I did such a great job that there are no questions. But if you guys do have any additional questions, feel free to email me. And yeah, thanks for listening.
Everyone for that wonderful talk, and thank you for attending this talk as well. We'll hope to see you back next semester. We have some exciting lectures planned up as well. So good luck, everyone, for the rest of the semester and for finals.
Thank you.